Hello viewers, in today's session we are going to discuss another important problem from domain of functions. And here in this session we are going to find out the domain of this function f of x, that is equal to cos inverse 2x minus 1 plus sine inverse x plus 1. So here we see that our function f of x is the sum of two inverse trigonometric functions, right? So here let us assume this function as g of x and this function as h of x, right? So g of x is cos inverse 2x minus 1 and h of x is sine inverse x plus 1, right? Now to get the domain of this function f of x, let us assume that the domain of this function g of x is d1 and the domain of this function h of x is d2, right? And the domain of the function f of x may be taken as capital D, right? So now f of x is the sum of two functions. Therefore, the domain of f of x, it depends on the domain of g of x and h of x, right? And here we have to search for those values of x which simultaneously satisfy or define these two functions, right? Or in other words, we can say that the domain d of this function f of x is the intersection of the domain of g of x and h of x. So d is given by d1 intersection d2. So here we have to search for all values of x which are common to the domain of this function g of x and h of x, right? So let us first find out the domain of g of x and then we'll find out the domain of h of x, right? So let us first consider this function that is g of x. So now from inverse trigonometric functions, we know that cos inverse theta has the domain that is theta belongs to the interval minus 1 to 1, right? And the range of cos inverse theta is given by this interval that is 0 to pi. So here cos inverse theta is defined for all values of theta lying between minus 1 and 1, including minus 1 and 1. So we can also write theta is greater than or equal to minus 1 but less than or equal to 1. So here in the function g of x, we have cos inverse 2x minus 1. So we can take for theta, we can take 2x minus 1. So let us substitute theta is equal to 2x minus 1 in this inequality. So we have minus 1, 2x minus 1, and here we have 1. So let us add a 1 throughout this inequality. So we have minus 1 plus 1, then 2x minus 1 plus 1, and here 1 plus 1. So here we have 0, here we have 2x, 1 and minus 1 get cancelled, and here we have 2. So let us divide throughout by 2. So we have 0 over 2, here we have 2x over 2, and here we have 2 over 2. So this is 0, this is simply x, and here we have 1, right? So the domain of this function g of x, that is cos inverse 2x minus 1, is given by this inequality, that is x should belongs to this interval that is 0 to 1, and here both the endpoints 0 and 1 are included, right? So let us here represent this interval on the real number lines. So here we have minus infinity, here we have plus infinity, here we have 0, and here we have 1, right? So x belonging to this interval 0 to 1 may be represented like this. So here we have this interval, and remember here both these endpoints 0 and 1 are included, right? So the domain d1 is given by this interval, that is 0 to 1. Now let us find out the domain of the function h of x. So h of x is sine inverse x plus 1, and again from inverse trigonometric functions we know that sine inverse theta, it is defined for all values of theta belonging to the interval minus 1 to 1, and sine inverse theta has the range, that is minus pi by 2 to pi by 2. So here again sine inverse theta is defined for this interval, that is the domain of sine inverse theta is given by theta greater than or equal to minus 1 but less than or equal to 1. So now if we compare sine inverse theta with the sine inverse x plus 1, so in this case theta is given by x plus 1. So substituting theta is equal to x plus 1 in this inequality, we have minus 1, then x plus 1, and here we have 1. So let us now solve this inequality. So we can now subtract 1 from throughout. So we have minus 1 minus 1, here we have x plus 1 minus 1, and here we have 1 minus 1. So here we have minus 2, here we have simply x, and here we have 0, right? So this inequality can also be written as x belonging to this interval, that is minus 2 to 0. And remember here minus 2 and 0, both the endpoints are also included. So the domain of this function h of x, that is d2, is given by this interval minus 2 to 0, right? So now let us represent this interval on this real number line. So here we have minus 2, right? And from minus 2 to 0, here minus 2 and 0 both are included, right? So here we have minus 2 included, and 0 is already included in the domain of d1. So we have this interval, right? So minus 2 to 0 may be represented like this, and here both the endpoints are also included, and similarly here 0 and 1 are also included, right? So now we have the domains of this function d, that is g of x and h of x, and now we have to search for the common region, right? So now if we look at this real number line, then we can see that here we have minus 2 to 0, right? And here we have 0 to 1. And from this diagram, we can see that this portion minus 2 to 0 is not included in the domain of D1. And this portion 0 to 1 is not included in the domain of this function h of x, that is d2, right? And the only common point that is that belongs to both the domains is 0, right? So here we have only one point in the domain of this function f of x, right? So d is now given by d1 is 0 to 1, and here we have the intersection, and then we have minus 2 to 0, and from these two intervals we can identify only one point which is common to both these intervals, right? And the point is 0. So 0 is included in both the domains. So here the domain of f of x consists of only one point, right? So here we have only 0. So the domain of this function f of x has only one real number, that is 0.